In the other course I have on my channel called the Global Carbon Cycle, I discuss a lot about how carbon cycle affects climate. And of course it comes through greenhouse gas effects, radiative perturbations, additional trapping of outgoing long wave energy, and so on. So you expect that volcanic forcing, which affects the radiation balance of the Earth system, is also going to affect climate and the carbon cycle. So it's going the other way. And there are many studies looking at corals and so on for the longer term volcanic activity. So here is the volcanic forcing of in terms of the stratospheric aerosol optical depths, which is basically the blocking of the radiation, let's say the solar dimming effects and so on. And you can see that there are concentrated activities during some times, like here in the 12th and 13th centuries, which turns out to be maybe a trigger for ending the medieval warm period, and then it was taken over by the solar minima. And when you have solar activity minima or sunspots being a minimum, the radiation is also minimum, because when you have more sunspots around them, you get more radiation. It's called plage. So you get more energy when there are more sunspots and less energy when there are less sunspots. So the transition from the medieval warm period, when the Vikings colonized Greenland because it was warm enough to do agriculture on the coast of Greenland and so on, then slipped into the Little Ice Age during the 15th, 16th, 17th century, and then presumably one of the reasons the Little Ice Age could have ended is that despite this chunk of volcanic forcing here, it's the industrial activity, coal burning, increased CO2, and maybe increased black carbon particles being deposited onto glaciers in the Alps and so on and so forth. Okay, so volcanic forcing is a part of the natural climate variability as best as we can understand. But one has to be careful as well making these links, unless they can be shown to be causal links and not just anecdotal links. So was medieval warm period really a global warm period? Well, you can see the reconstructed patterns here, again showing statistical significance and data density and so on. This is the medieval climate anomaly from this side here. And you can see that there was plenty of warming in the North American European sector, with some warming over in the Middle East and maybe over the Pacific and the gyres over here and so on and so forth. But it's by no means a uniform global warming pattern. Maybe there was also some Arctic amplification which happens in the current global warming as well. And this could also be interpreted as maybe a perturbation to the jet stream pattern. So if jet stream keeps on getting more wildly perturbed, maybe you can have a low frequency rectification which looks like cold, warm kind of pattern. Wow. Just the way to remember it is that medieval warm period did have a large impact here in terms of Vikings making all the way here and even into North America. Eric the Red's son Leif made it all the way here according to all the evidence available. The transition to Little Ice Age, again, the warming here seems to have remained. Evidence of cooling happens over North America, but a lot of evidence over the European and Eurasian sectors. There is lots of documented evidence here as well, freezing of the channels over the Netherlands and so on and so forth. Okay, so that's the natural forcing. What's happening in general is to then try to see that dynamic patterns, dynamics of the ocean atmosphere coupled system, including vegetation response, carbon cycle feedbacks and so on, create dynamic patterns. So even if CO2 forcing is quickly mixed and becomes hemispherically uniform, the radiation imbalance actually ends up being distributed based on, again, the equator to pole temperature gradient. So under global warming, the warming near the tropics, where temperatures are already pretty warm, is not as strong as in high latitudes, where cloud radiation feedbacks and ice albedo feedbacks amplify the warming, and we get what is called Arctic or polar amplification, which is somewhat different in the Antarctica because of the differences in ocean land configurations. Nonetheless, we have to remember that even if we do radiation perturbation because of let's say geoengineering, we have to be aware of how the dynamic patterns may evolve, and even if you do it in one place, you may end up creating unintended consequences in another place. So here are the examples of other effects. This is the El Chichon Pinatubo being shown here just before the big 1982-83 El Nino and just before the 93-94 El Nino. And there are observations and various model estimates here of the 12-month moving ozone anomaly over Edmonton, Canada. And you can see that the volcano does have an impact on the ozone hole or the ozone anomaly over this high latitude, which is where you typically want to look at it because of the polar stratospheric chemistry that is special in the stratosphere. So that's something to be very keenly aware of. You don't want to create any damage to the ozone hole, which we mentioned also in the case of supersonic transport and the U-2 plane flying in the stratosphere and so on and so forth. Modeling experiments show that Pinatubo-like warming does produce these dynamic patterns of winds at 850 hectopascal, which is just above the planetary boundary layer at about, let's say, 1 kilometer height. And these are changes in the zonal winds. So here you have the jet stream perturbations, the subtropical and polar jet streams. So you can see that if you double the Pinatubo kind of forcing or halve the Pinatubo kind of forcing, you get almost a linear response in the atmospheric circulation response, and that can explain the kind of patterns we see in these warmings, no matter what the radiative forcing cause is. So we have to be aware of the global impacts. The other impacts include ocean acidification and impacts on corals, which is shown here from this paper with data on lanthanum calcium. And this is lanthanum and yttrium, aluminum, calcium, and so on and so forth. So you can see the data coming along before the eruption, Pinatubo happens, and then you have a huge drop. So this is interpreted as the impact of volcanic eruption on corals, which is not good news, of course. And if you take these kind of effects and remember that ozone is going to affect other things as well, including the circulation, then we have to be very careful about the geoengineering. This is work by Trenberth and Dye, which used data to look at the evolution of droughts before and after the Pinatubo eruption, and argued that the global extent and the strength of the droughts following the eruption were one of the strongest in decades. So it definitely had an impact on radiation balance and precipitation distribution and created global droughts. You don't want these kind of things happening. Look at the strength of the Palmer's Drought Severity Index here. If you don't know what that is, you can look it up, but basically it uses temperature and soil moisture and precipitation and so on to say how far we are from normal distribution of these. So it's a drought index, and you can see that the patterns are quite global. The other thing is the impact on carbon cycle I mentioned. So this is going to have an impact on vegetation, which is going to show up in carbon cycle. So just the CO2 put in by the volcano is not significant enough to affect the carbon budget, as you can see here. You barely see any blips in the data by the volcanic eruption itself. It is just the fossil fuel emissions and the seasonal cycle that are seen here. But if you take out the seasonal cycle and the trend and do interannual variabilities, you can use combination of models and data. I won't go into the details, it's a detailed figure here, but you can see the simulated volcanic induced atmospheric CO2 changes with Agung in the 1960s, El Chichon in the 80s, Pinatubo in the 90s, the radiation effect and the reduced cooling and reduced radiation actually ends up reducing heterotrophic respiration of carbon from soils and vegetation. So atmospheric CO2 is actually reduced and land sequestration of carbon is increased. So atmospheric growth rates are affected following the volcanic eruptions, but the key thing to notice here is the multivariate El Nino index. So the impact of the volcanic eruption tends to depend on whether it happens before an El Nino, which tends to have its own impact on the carbon cycle because of the changes in trade winds, in upwelling, in precipitation distributions, droughts, wildfires, and so on. Or whether it happens before a La Nina, which is not exactly symmetric to El Nino, but it tends to create more rainfalls and reduced wildfires and so on and so forth. Okay, so there is a latitudinal dependence of volcanic eruption because it decides how much will get into the stratosphere, and there is this El Nino dependence because that depends on what background state the volcanic eruption is acting. Okay, so these are the various estimates, again showing that fossil fuel emissions dominate and land use emissions come after that. But the extraction of the impact of volcanoes on global carbon sinks and airborne fractions can be done reliably compared to data from models. And the main message is again El Nino dependence and the fact that global cooling affects the impact of volcano on the carbon cycle in terms of reducing respiration, increasing carbon storage in land, reducing the atmospheric fraction. I have one more point to make about the cooling after volcanic eruption, which I will add in a minute. So I should have said this before, but I forgot. So here is the figure. In general, there is a systematic cooling at a global level, even though we looked at the patterns and how complicated they are and the jet stream impacts and so on and so forth. The best way to look at it is to look at the years before a number of volcanic eruptions. The best data you can get is by taking the composite, because usually there are lots of noises happening in the global temperatures. There is El Niños, La Niñas, and so on. But if you take a number of volcanoes and look at the years before and the years after, you can see that there is natural variability happening here. It is with respect to some baseline you can use. But after the volcanic eruptions, typically the temperatures cool by various amounts, surface temperatures, because of the radiative perturbations, and it takes several years before that volcanic impact is completely removed and you get back to natural variability. So there is no doubt at all that, especially for strong volcanoes like Pinatubo, there are strong global cooling patterns which obviously would impact crop yields and so on and so forth as well, which has to be studied, and there are some studies. And the year without summer in 1816, with the global cooling of half a degree, is blamed for crop losses over England and many other parts of the world that we looked at. Again, that is argued to be not necessarily related to volcanic eruptions, but this figure of multi-year cooling would say that that is potentially related to the volcanic eruption Tambora in 1815. Okay, so that kind of concludes our story of how volcanic eruptions perturb the entire Earth system that we talked about, the concept of Earth system. So whenever we do geoengineering of spraying aerosols into the stratosphere, We have to be keenly aware of what are the cascading effects and which one are to be really, really avoided.